PowerPoint slides since I'll be out for probably 2 days. So if you look at, I guess the first thing we'll start off with is Q10 and reaction rate. You did some Q10 problems while I was gone, and I like this graph a lot because it sort of relates it to rate of reaction. And if you think about it, what we're really talking about with changes in temperature, especially with ectotherms, is that as you increase the temperature in an ectotherm to a point, their reaction rates will increase also because you're creating metabolic energy, which allows better collisions with enzymes, so you're getting more things done in the body. Now, you guys remember that Q10 is usually between 2 and 3, so if you look at the light blue line in the graph, you see that Q10 is about 3, and on the dark blue line, you see that Q10 is 2. Now, if you went over to, let's say, 30 degrees and you moved up, and where the blue dot is at the reaction rate, rate of reaction of 4, if you come across there, you see that for 30 degrees at a rate of reaction 4, along the dark blue line, you have a point there. If you go to the left, though, and intersect the light blue line, you'll see that that same rate of reaction would, at a Q10 of 3, would happen at a much lower temperature. So if you're comparing two organisms' metabolism that were, let's say, ectotherms, you could easily do that using this graph, and you could talk about how basically as Q10 increases, as the slope of the line gets quicker, or steeper, the temperature needed for the enzyme reactions to take place is usually lower. But the more the less steep the slope is, the more energy is going to have to be put into the environment for the organism to absorb so it can do biochemical reactions. If you look at the red line at the bottom, you're seeing an organism sort of like an endotherm because they maintain homeostasis. Normally, if it's within range of what they can handle, their Q10 is going to be very low because obviously they're keeping a balance of their body temperature. And even if you increase the temperature of the surroundings, their internal rate of reactions may not change at all because they've got that thermal inertia built up. And that may change if the temperature gets out of the range that the organism can tolerate. So just a little bit of an example of how you can use Q10 in comparing organisms. So we're going to move on to energy budgets. And just like having a money budget, it's an amount of energy that you can use for a specific thing. And organisms aren't conscious of this, but those that are more successful budget their energy much better. So if you look at this slide here, we see at the top, for various organisms, the annual total energy expenditure. And so you see for a mom, 60 kilogram human from a temperate climate, she's got a pie chart that shows a lot of energy stored to her resting basal metabolic rate. And then, of course, the next biggest thing is activity. But there's a lot of other costs in there because she's an ectotherm or an endotherm. Energy towards reproduction. So like if this woman is pregnant, so she's having a lot of her energy devoted to her baby. Also for her temperature regulation, her metabolic energy is a pretty big cost. And since she's adult, that her growth costs are not real big. Now for you guys, you'd probably get rid of the reproduction part of the pie and you'd increase your growth, and that would be maybe a better representation of you at that same kilogram amount. If you look to the other endotherms, you have a bird in the middle. So their pie chart looks a little bit different. So they have to be much more active and devote a lot more energy there, and they're a lot less at rest at 4 kilograms. So remember, as body size decreases, your activity, your metabolic demands are going to increase. If you look at the smaller deer mouse there, then the deer mouse has a much lower annual energy expenditure, And this deer mouse then is going to devote most of its energy into temperature regulation because it's so small. If you take that over to an ectotherm, you can see that if you compare the ectotherm to the penguin, you can see that their pie graphs are a little similar. You've got a reproductive cost very similar to the penguin. You've got a BMR really similar to the penguin, and you've got high activity. But for the ectotherm, you have a specific amount of energy that's going towards growth because those organisms are being grown outside of the body in an egg. If you compare that to, let's say, a human, a lot of that growth is for the female is devoting that to her baby. And so because the python reproduces outside of the body, it's spending a lot of its energy growing and getting bigger because it's not growing inside like a mammal would have growth inside for its baby. If you look at the bottom, then remember about body size and energy allotment. You can see that the energy expenditure per unit mass is pretty high for the deer mouse, being the lowest mass. And as you go in terms of the endotherms anyway, the human with the largest body mass would have the lowest total energy expenditures per mass, which is what you would expect. And then if you look at the ectotherm, the python over there requires much less energy per kilogram because it's getting its energy from the environment. It's not having to produce its energy by itself. All right, so nice little slide here for energy budgets and the different requirements that organisms have based on their adaptations, their niche, and what type of organism they are. So I would say that this is a pretty important slide to understand. Okay, so just in summary, a male penguin spends a much larger fraction of its energy for activity because they have to swim to catch food. Female deer mouse spends a large fraction of the energy for temperature regulation because it's so small. And then if you look at the ectotherm, the python doesn't really have a whole lot of temperature regulation costs because of the environment. And it grows continuously through its life by shedding its skin, growing inside, shedding its skin. Okay, so just another example of the last slide. So for some concept checks here, you want to make sure that you understand these, and I'm happy to go through them in class. So take a look at them, and you can pause the presentation and take a look at them and jot down questions if you have them. So I'm not going to read these to you and answer the questions because I want you to try to do that. So if you have questions, write them down and we'll talk about them first thing when I get back. Okay, moving on to one of the things I think is kind of cool is how organisms regulate and conform to their surroundings. So the two extreme behaviors that organisms can take is regulating their body temperature or regulating their metabolism, and then the other one is conforming. So this is how, when the environment changes, the two main ways that organisms would cope with that on basically two different ends of the spectrum. So if you're a regulator, then basically you're using your internal feedback mechanisms to control your body as the external environment's changing. Okay, so it could be temperature, but it could be other things too. If you're a conformer, then this allows your internal condition to vary as the environment on the outside changes. So if you're a fish and you're in a lake and the lake water gets heated on different times of the day, then you'd have to swim around to the different temperature water to conform so that the energy of the system, obviously, since you're an ectotherm, is going to help your metabolism heat you up or cool you down. Okay, so no organism is a perfect regulator or a perfect conformer. Even an endotherm like us, if we get too hot, if we're outside, maybe we would sit in the shade and cool down. And you know, even some conformers can regulate their temperature a little bit, even though they have to move around. Um, Also, you know, most organisms that are endotherms, as you know, are going to maintain their homeostasis. So they're going to have blends of positive and negative feedback in their body, which allow them to be regulators. And then, of course, you've got homeostasis also in ectotherms, and they're doing this by um, changing their metabolic activity with a response to the environment. So then we get to basically the crux of it, which is homeostasis and feedback. So you guys know at this point that you have homeostasis in an organism being the regulation of the internal body or the cell, depending on what level we're talking about, as the external environment's changing. So there are three components to this: receptor, control center, and what's called the effector. The receptor detects the change in some sort of internal environment. So let's say, to make it easy, we'll say body temperature. The control center processes the information and it directs the response by the effector. The effector would be the part of the body that's eliciting the response. So you can have negative feedback, which we talk about a lot, and this is something that prevents the change in the particular direction. Now this could be in a positive direction or a negative direction. So for example, if your body is getting too hot, that's an increase of positive feedback in a specific direction that's being amplified more and more and more. But that's in a positive direction because temperature is increasing. So you might have some body responses to that to put the brakes on that. On the other direction, you could do it too. So you can have positive feedback in a negative direction. Let's say your body's cooling down and it's getting colder and colder and colder. That's still a direction, even though it's negative. So your body maybe would want to put the brakes on that too, so you can stay within the range that you need to for your metabolic processes to take place so you could stay alive. So positive feedback involves a change in some variable that triggers a mechanism that amplify rather than reverse changes. So most organisms that use homeostasis operate on the idea of negative feedback. If you are an organism like a human, then you've got very intricate controls that involve lots of organs and hormones and things that we'll talk about in a second that very specifically regulate the things like temperature, oxygen amount in the bloodstream, maybe other chemicals. Whereas, a organism that is more like a conformer, they might not have the same type of delicate homeostatic equipment in their body, since they are moving around trying to regulate themselves by going in and out of different conditions in the environment. Okay, so our body temperature is kept close to a specific set point, and we have certain negative feedback mechanisms that cooperate to do this. You can think about, and your book does a good example of giving this analogy, you can think about your body as a thermostat, just like in your house. And if you set your thermostat in your house to, let's say, 70 degrees in the wintertime, the thermostat is going to maintain homeostasis in your house, even though the outside temperature is changing. And so you have different components to that. You have a furnace, you have ductwork, you have sensors that are in the thermostat. So when it gets colder outside and your air temperature in your house is going to get colder, then obviously the coldness of the air is going to trigger the temperature receptor in the thermostat, and that's going to send a signal to your furnace. Your furnace is going to burn more energy. It's going to heat your house. If your house gets heated up to that certain level, you don't want to waste energy, you don't want to overheat the house. So when it gets up to 70 and maintains that homeostasis, the negative feedback mechanism kicks in and stops your furnace from working again. So your body is very similar to that. And of course, remember that unlike a house that has a source of energy from, let's say, natural gas, your body has to get this energy from food. So you can see pretty easily that as homeostatic demands increase, the organism is going to have to eat a lot to satisfy that. And you can think back to that little shrew or that little deer mouse. They have such a high metabolic demand because obviously they're losing a lot of heat. So their thermostat is being triggered all the time. They have to turn on the furnace, so to speak, to keep their body temperature at a high level so they can keep their reactions going, which means they've got to forage and eat a lot. Okay, so here's an example using body temperature. So over the short term, we've got homeostatic mechanisms that keep the body temperature close to your set point. So my body temperature is a little bit low. It's in the 97 range. Some people it's right on 98.6, but whatever it is, your body is trying to keep it at that level. So of course, you've got changes that can happen on the surface of the body, which can cool down and heat up. But that's not really changing your body temperature a whole lot. So over the long term, you also have your internal environment that has to stay constant. So there may be different homeostatic mechanisms that control that. Here's a nice picture from your book, and this is a thermostat function of a organ called the hypothalamus, which is located in your brain. And so if you start at the brain at the top and you look at the homeostatic mechanisms. Actually, let's go into the middle where you see homeostasis. Internal body temperature being kept constant. So if we follow the cycle to the right, or to the left, I should say, if you increase your body temperature, so let's say you're running to class because you're late or something, or you're outside in the hot weather, this is sensed by mechanisms in your skin or other receptors. The thermostat in your hypothalamus activates the cooling mechanisms, so that causes sweat, blood vessels to dilate, so heat can be dissipated from the skin surface. And as a result of that, if you follow around to about 3 o'clock on the right side, your body temperature decreases, the thermostat shuts off the cooling mechanisms, and you're back to where you started. On the other hand, if we look at the lower cycle, if we go to the right now, if you're outside and let's say you went to Snow Mountain over the weekend, you're playing in the man-made snow, and your body temperature is decreasing because you're getting cold, then the thermostat in your hypothalamus will activate sort of the opposite idea, whereas you're going to warm the skin. So blood vessels constrict, and it's called vasoconstriction, and that's going to keep your body temperature inside your body. And then you have muscular contractions, which cause shivering, which generates metabolic heat. Hopefully that heats up your body and you go back to your homeostasis in the middle. So just like your house, cooling and heating as the outside temperature increases or decreases, the thermostat would be like your hypothalamus, and your positive and negative feedback mechanisms are regulated inside the body. Really good slide, I think. All right, and then so if you look at feedback inhibition of enzymes, you can see, compare the idea. So on the right, we have the thing I just talked about. And on the left, then, you see this old picture that we've seen before, where you have enzymes doing different reactions, and then they have an end product, which actually is the negative feedback mechanism for the enzyme so that the process doesn't happen again. So I just wanted to show you a comparison on two different levels, this idea of negative feedback. All right, so what question you might want to ask is, how does this type of negative feedback differ from that in regulation? Does it differ? Is there a specific difference? So think about that, and if you don't understand this or you have questions, be sure to bring that up in class as well. All right, there's a short video on feedback, and you can check that out on your own. I think it's pretty good, but I'm going to keep going here. And then the last thing to talk about is this idea of thermoregulation. So we already talked about this a little bit, but if you look at other organisms, let's say you had a mouse and a small lizard. So one is an endotherm and one is an ectotherm. You're putting them they're at the same mass, you're putting them both at rest, and you're going to do a temperature experiment on them. So the question is, which animal would consume oxygen at a higher rate? So that would be a great short answer question. If a mouse and a small lizard, the same mass, both at rest, were placed in experimental conditions, which animal would consume oxygen at a higher rate? Okay, and so if you think about this idea, the small lizard, under the same environmental conditions, should have a higher Q10 value because as it's being heated up, it's going to have higher metabolic functions, which requires the organism to consume more oxygen. All right, so thermoregulation, as we just mentioned, is a way for organisms to maintain their homeostasis. On the left side, you see a nice little picture of body temperature of an endotherm versus an ectotherm as the environment changes. So as the environment changes, the river otter, pretty consistent. If you look at the fish, the bass is going to be, its body temperature is going to change with the environmental temperature. So it's not generating much metabolic heat at all in its body. It's getting its heat from the water temperature, and it's a conformer. On the right side, you see just a nice graph showing the different kinds of thermoregulation. At the top and the bottom, you see the two extremes, the endotherms and the ectotherms. And then on the left and right, you see two other categories which really aren't that important to know, but just a nice separation of heterotherms versus homeotherms, those that keep their body's temperature constant versus those that allow their body temperatures to fluctuate. Heat exchange, you can have heat exchange in the environment in a lot of ways. So you can radiate heat. So organisms that have large surface areas will tend to radiate heat. You see like jackrabbits have big ears, or this lizard has a very broad body to radiate heat. Evaporation. This lizard's only evaporating probably from the moist surface of its nose, but in an endotherm like us, that would be sweating. Convection, so we've got the transfer of heat past the surface. So that would be going back to our original talks about water with evaporative cooling. And then conduction. You can absorb heat from your surroundings. So a lot of lizards and things will lay on rocks and they will absorb heat from the rocks and surfaces so their metabolic functions work better. All right, here is an ectotherm behavior over a specific time of day. So you've got basking of this lizard, and the behavior of the lizard is going to change as the temperature changes also. So the squiggly blue line is the body temperature of the lizard, and then you've got the air temperature near the ground, and then you've got a burrow. So during the day, or at the very beginning, the lizard's in the burrow. It hops out of the burrow. It starts heating up its body by basking. The metabolic energy, it gets elevated. It can do things like forage or whatever like that. At the heat of the day, the lizard's going to go to the shade. And then as it gets really hot, the lizard's going to return to its burrow, and then it'll stay there all night because the burrow is probably not cooling down as fast as the air would. An endotherm, in contrast, you're going to have its metabolic rate having a upper and lower limit, and where the line is level on the dotted line, that's our body temperature, like for us, that we would be able to maintain. But anything above that or anything below that, we're going to have to change things in our body to compensate. All right, so if endotherms generate heat, how do they get this heat? Well, the main way they do it is through energy from the things they eat. But sometimes you have organisms that generate heat by something called brown fat. Brown fat is located usually in the shoulder back region of some organisms. And this brown fat is really interesting. It's got a ton of mitochondria and lots of capillaries in there. And so, so this is not just fat droplets, it's tissue, it's adipose tissue, but it's got a combination of the mitochondria and capillaries in there too. And when an organism needs quick heat production, it can burn this fat really quickly, which gives fuel for the mitochondria, and that heats up the body temperature. And so you find this in a lot of small mammals and hibernators like bats, small shrews and mice and things like that, where they need to heat up really fast. Now, in contrast to that, we have a lot of organisms do shiver, but in these cases, the skeletal muscles are going to be burning ATP, and that burning of ATP releases heat. So when you're shivering, the way your body is trying to heat itself up is by breaking ATP into ADP, and you're releasing heat. So pretty neat two examples of heat generation in mammals. All right, I'm going to skip through this experiment. You can read through it. It's a great example and would be a fantastic short answer question for the AP exam. So again, read through it. And the what if at the bottom has a great question. This would be more like a DBQ kind of multiple choice or short answer. And so please ask questions if you have them. All right, so what I want to sort of skip through here is to the last thing, and that is hibernation and torpor. Okay, so some organisms have to conserve energy when it's cold outside. And so torpor is an adaptation that allows them to go into a suspended state of low energy, and their metabolism decreases. Now, it's a little bit different than hibernation. Hibernation is long-term torpor. So short-term torpor would be an organism lowering its body temperature, but coming out of it to forage and then going back and lowering its body temperature. Hibernation occurs over a longer period of time, so a whole host of metabolic processes get turned way down in terms of sort of the dial, and you dial it down for a long period of time. And some of these temperature reductions in the body can be pretty dramatic. So you can get organisms, mammals, cooling their body down tremendously in terms of what they can tolerate, and they won't freeze. They will allow their bodies to get cool, but since they're not trying to heat their body, as long as they stay above freezing, they don't have to worry about cell damage. And what this does is it saves the amount of energy that they have to burn, and they're not doing anything, obviously, so they're not maintaining that body temperature they normally would. But as they survive for the long periods of time on this limited energy that's stored up, then when conditions are better, they can come out of torpor, and since there's probably food available, they can go and find their food. So here we have this little Belding's ground squirrel, and it's the same graph basically. You can see at the bottom the torpor where as the spikes dip to the bottom, that would be the torpor, and where it says arousal, that would be where the ground squirrel's coming out of the burrow or eating during the winter and then going back to sleep. And so this is happening a lot of different times over the season. So this is a daily hibernation pattern, but it's not long-term hibernation where the ground squirrel will be hibernating for weeks and weeks and weeks. So this squirrel is coming in and out of torpor, whereas a true hibernator is going to stay that way for a long period of time. Okay, so this is where we would leave off in metabolism. So I gave you a lot to think about, a lot of things to ask questions about. So please look back over it. If you have questions, post them on Edmodo or please ask them in class. See you tomorrow.